Okay. Now, so what would you suspect is going to happen? What would you suspect is going to happen to the atomic radius? Let's put the atomic radii in. Red, you want to read that again? You did that very well. Look at the atomic radii, and I want to look at the third period. Look at sodium to argon. Let's put in the numbers from sodium to argon. Go ahead. What is it? I can't hear you.
What are we doing?
We're doing the atomic radius, upper right-hand corner of each individual square from sodium to argon. Okay?
Okay, yeah, okay.
You got it now? I know there's a lot of data in those little squares. I agree. So what do you got?
191.
191. What's next?
160.
160. What's aluminum?
143.
143. All right. What about silicon?
109.
109. Okay. And phosphorus is the same, isn't it? Yeah. 109. And sulfur?
105.
105. And then chlorine?
102.
102. And then argon?
94.
94. So you can see what's happening. What's happening to the atomic radius as I go from left to right across a period. We suggested that the ring will collapse in on itself, correct?
Yes.
And that's exactly what happens.
Yes.
It starts out at almost 200. And then it collapses to almost 100. Below 100, yes? So it's significant, isn't it? It's a significant drop. It's a significant drop. Remember, it's the atomic radius, the shielding effect is constant. So what is involved when what's limiting here as you go from left to right across the period? What's the limiting factor? What's it really based on? It's based on the nuclear charge, isn't it? Yeah. As you're going down, what's key when you're going down the column? Nuclear charge or shielding effect? Really shielding effect, isn't it? The fact that it goes down less and less is really shielding effect, right? Shielding effect and nuclear charge. But the fact that it's bigger, not how much bigger, just bigger, is basically shielding effect, isn't it?
Yep.
Yeah. Okay, now, the trend for ionization energies is going to be, the trend of ionization energies is going to be what as I go from left to right? If this is being held more and more tightly, that ionized electron, that electron is being removed, is going to be what? Look at your graphs. Take out your graphs now. Or no, what page is that graph on?
It's on page 178.
178 is that graph.
There's another one, sir.
Okay. Is 178 a good graph?
175 to 178.
Okay, 178. Is that the graph? Okay, 178. Okay. Look at 178. Do you see that in the particular period, let's say period 3, what's happening to the ionization energy? What's happening to it? It's as you go from left to right across a period, Will? Yeah, it's getting higher and higher, right? Why? Because these electrons are becoming more and more stable. That final electron that you're adding is becoming more and more stable. The more stable that electron gets, the lower its energy, right? The lower its energy, the more energy you need to remove it.
Yes.
Right? Isn't that, you get that connection? Yes? So this, right? But are there exceptions to the rule, or are there exceptions to the trend of increased ionization energy as I go across the column? Are there exceptions to that?
Yeah.
Yes, there are, and this is key. This is key. Very big. What are those exceptions Are they really exceptions or are they apparent exceptions?
Apparent.
Yeah, they're apparent exceptions. There's a real reason why they occur, and those apparent exceptions could actually be predicted, couldn't they? Yes. And what principle are they based on? The Aufbau principle. That's correct. For instance, let's look at 2 and group 2 and 13. This is very important, guys, and I'm going to make this clear in a moment. It's not element 11 and 12. Bear with me here for a second. It's not element 11 and 12. That kind of gives you the idea that they're right next to each other, which they are, but it's group 2 and 13. Look at your periodic, go back and look at your periodic table. So in other words, look, here is right. This is the electron that I'm removing for boron, right? That one right there,
Yeah.
right?
Yeah.
Yes. This is the electron. This one doesn't exist for beryllium, and that's the one I'm removing for beryllium, right? So the Aufbau principle says that that electron there is a lower energy state than that electron. It's lower. It's a lower energy state. So it takes more to remove that than it does that. It doesn't take as much to remove that. So look at your graph. Is the ionization energy higher for which electron? Is it higher for this electron because it's farther across the periodic table? Or is it lower? It's lower. But couldn't that be predicted based on the Aufbau principle?
Yeah.
That full S is more stable than the full S in a very, very partially filled P?
Yeah.
So the Aufbau principle would predict that the ionization energy for that electron is actually indeed lower instead of higher. And the same thing is true for magnesium and aluminum. That could be magnesium and that could be aluminum, correct? Yes? Now, look at your graphs, and this is big. This is why I wanted you to bring your graph. Okay? Look at calcium and gallium. That's 20 and 31. So they're not next to each other number-wise. It's not 4 and 5 or 12 and 13. So if you look at your graph, or that graph on page 178, see if you can find 20 and 31. Now, according to Aufbau principle, right? According to Aufbau principle, let's see. This is the Aufbau principle. Let's see. If I just look at the S and P's, right? The S and P's, right? This is the same thing. Right? 20, that's calcium, right? Right?
Yeah.
And then that's going to be gallium, right? Isn't it the same thing? Yeah, there's a lot of D's in between them, aren't there? There's 3D10 in between, right? Right? But isn't it the same Aufbau principle? So you tell me, according to the trend, as you go from left to right across a period, the ionization energies increase. I'm asking you, is that true if you compare calcium with gallium? Is gallium higher, or, as the Aufbau principle would predict, gallium would be lower? Is gallium lower ionization energy? Yes, it is. Look at the graph. Very good. It is. The gallium is lower. 31 is lower than 20, isn't it?
Yep.
It is. 31 is lower than 20. You see that now, Victoria?
Yeah.
I know, the graphs are not the greatest. That's why I wanted you to bring your own, because it's bigger. It's easier to see it. See that? Yeah? Get it? Okay, now. So, every peak and valley, every peak and valley you should be able to reason why they're there. You should be able to reason why they're there. I want to do ionic radius and electronegativity still. I'm going to go back to ionization energy, but I'm going to make sense of all of this. Okay? But I want to keep it running. Is that okay? Is that okay?
Yep.
All right, now, let's look at the ionic radius and the trend for ionic radius. Let's say that carbon, or in this case, silicon, that these are going to give up electrons to have the valence structure of what noble gas? Neon. Look, if this gives up one electron, what is the noble gas? It's going to be neon, right? Isn't it?
Yeah.
So these are going to be cations, aren't they?
Yes.
I know I say +4 instead of 4+. I just never got into that. The way they do it, I'm a rebel. I know. I'm such a rebel. Okay. So in other words, this doesn't exist, right? Okay? That doesn't exist. You see that? You see that? Does that make sense? Does that make sense? Now these are going to gain electrons to be like what? To be like what noble gas? Argon. So you're going to keep that ring, right? So that's going to be -3, -2, -1, right? Yes? 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 Okay, good. So now look at this. Is identifying the trend of, let's say, decreasing radius, ionic radius, as straightforward as atomic radius? No, it's a little bit weird. But it's doable. It's doable. It's doable. First of all, these are the cations. These are cations. Right? And these are anions. Right? What group of ions will be larger? Cations or anions? What group will be larger? Cations or anions? What'd you say? Okay, so cations are larger. So something with 2 shells will be larger than something with 3 shells? Does that make any sense to you whatsoever?
Not even.
So something with 3 shells is going to be much smaller than something with 2 shells.
No.
Would you like to revise your answer?
You wrote anions there.
I wrote it, that's right, I wrote anions here. What's going to be larger? Anions or cations?
Anions.
But you said cations. Are you revising your answer?
What?
I said anions.
No, you said cations. You said cations are larger. Do you understand why that couldn't be possibly correct? It almost sounds silly, your answer, right, to you, right? Excellent. Excellent. That's what I was looking for. I was hoping you were confused, not completely... Nah. Okay? All right, now, these have the same valence shell, right? So what would you predict would be the trend going from sodium to silicon? Would it be decreasing, increasing, or would they be the same? Shielding effect is constant. I'll help you with your thought process. I will think for you, okay? So this is nuclear charge 11, this is 12, 13, and 14. Nuclear charge is increasing, okay? Shielding effect is constant. They all have same valence shell. Okay. So is this going to be larger? Is this going to be larger? Same? What would you say the trend will be? Will it be decreasing radius or increasing radius? Don't answer right away. Give it 5 seconds. Think. What do you think? What's your answer? Anybody? Antoine.
Increasing.
All right, now I want you to think back. I want you to think back to long ago in a galaxy far, far away.
Oh, I get that.
Okay? Just 10 minutes ago. Okay? In a classroom right here. And we said that the atomic radius, where the shielding effect is constant, and the valence shell was 3, that ring, we said that the shielding effect was constant, didn't we? And we said the nuclear charge, as the nuclear charge increases, that ring is drawn in upon itself, isn't it? Right? Isn't that the same here for these 4, the cations? That this is all the same valence shell, all the same ring, right? Yet look at the nuclear charge here. The nuclear charge here is 11. Here it's 14. So the nuclear charge is increasing. So what's going to happen to that ring? Is that ring going to be drawn tighter, or is it going to expand? It's going to be drawn tighter, isn't it? Yes, you get that?
The thing is, you said that there were the same number of valence shells, but for sodium you have 2 circles and
But this has 2, the valence shell for sodium, ion, for the ion is 2, right? Just like neon. The valence shell of magnesium is 2, just like neon. The valence shell of aluminum is 2, just like neon. The valence shell of silicon is 2, just like neon. Are you confused still?
I get it.
Are you sure you get it? Is that, I get it, I'm tired of being questioned, or do you get it, get it?
No, I get it.
Okay. Okay. So it's the same valence shell, right? So if all else was even, they'd all have the same radius, right? But this nuclear charge is larger than this, right? About 20% larger, right? So this is going to draw that ring in on itself more tightly, isn't it?
Yes.
Shielding effect is constant. So what would be larger, sodium or silicon? Sodium would be larger. So decreasing would be sodium to silicon, okay. What about the anions? What would be the largest anion? Remember, same. How many electrons does each ion have here? How many electrons does each ion have? They all have 18, right? Because they all want to be like argon. They all have 18 electrons. What's the only difference between phosphorus, sulfur, and the number of protons, right? And neutrons too, but we don't care about the neutrons because they're neutral. So what's going to be larger? Phosphorus or chlorine?
Phosphorus.
Very good, Antoine. Phosphorus is, you said that spontaneously. Phosphorus is going to be larger because it has a smaller nuclear charge. They all have 18 electrons. I kind of purposely left that out here. These all have 10 electrons, right? Yeah? Because I was trying to say it was like neon. Yeah. Does that make it sound a little bit easier? When I say they all have the same number of electrons? They all have 18 electrons. Yeah? Oh, this has 17 electrons. This is, no, they all have the same number of electrons, right? Okay, could you hold your question until we're done? I want to get through this. We got like 8 minutes left. Okay, so the trend would be going from largest to smallest would be what? What's first? What's the largest in the entire line? What's the largest? Did it just end?
Sodium?
Did it just end?
No.
You're still going?
Passing out.
No,
Still going? Good. Excellent. So is it all on there too, by the way? No, not the whole thing, just the stuff we're working on.
Oh, yes.
Okay, good. My videographers are asleep at the switch, are they? Very good. You're paying attention to me, which is a good thing. So, it would be, what's the largest?
Sodium.
No, phosphorus. Yeah.
Phosphorus?
Anions above.
The entire period. The largest would be phosphorus, so it would be phosphorus, then sulfur, chlorine, then,
Argon.
no, argon's not an ion. What is it? Sodium, and then silicon smallest, right? Does that make sense?
Yes.
Okay, now, let's put in let's put in the electronegativities and see if there's any trend we can spot with shrinking radii, increases in ionization energy, shrinking atoms. Okay, let's see if there's anything there. Okay, who's here? Who's Antoine? Can you speak loudly? Can you open up to the electronegativity chart, which is on what page? Right here, 181.
Oh, this one.
Okay, Antoine, 181. You got it?
Yes, sir.
Okay, give me the first group. Give me alkali metals. Give me the electronegativity. What's hydrogen?
2.1.
2.1. What's lithium?
1.0.
1.0. What do you think the trend is going to be for electronegativity? Remember, electronegativity is the attraction for the bonded electrons. So you're looking at a bonding site, right?
Yes.
So what's going to happen to that electronegativity? It's going to probably decrease, right? So let's see if it's true. What about sodium?
0.9.
Oh.
Okay, Antoine, are you with me?
Yes.
All right, what do you? Can only Antoine answer? Antoine, what do you got?
0.9.
0.9. What about potassium?
0.8.
0.8.
0.8.
37 is rubidium.
0.8 as well.
0.8.
Yes.
And cesium.
0.7.
And francium's not there, is it?
No.
Okay, good. So what about here? Electronegativity for sodium.
Sodium is
Well, we have it here, right?
0.9.
0.9.
0.9. Let's just put 0.9. And then magnesium.
1.2.
So as you go across the period, it should increase, right?
Yes.
Yeah, it should. And what about aluminum?
2.0. 1.5, sorry.
Silicon.
1.2. 1.8.
Phosphorus.
2.1.
Sulfur.
2.5.
Chlorine.
3.0.
And then argon doesn't exist because it doesn't bond, right? Let's go back in and do, before we look at the electronegativities, let's go back in and put in the Ionic Radii. Look at the Ionic Radii, okay? Will, Ionic Radii, lower left-hand corner, page 180. Isn't it the lower left-hand corner? Okay? No, lower left-hand corner, right? So what's the Ionic Radii for sodium? Go across, sodium.
95.
95.
Yes.
Magnesium.
66.
Aluminum.
51.
Silicon.
41.
Phosphorus.
212.
Sulfur.
184.
Chlorine.
181.
Okay? You see that? How that is significant. You see the cations? They're all smaller than the anions, aren't they? You see that? And they shrink. You see that? So that makes sense